Buongiorno a tutti. Good morning, sorry. Good morning, and thank you for being here. We are very, very excited to have a Professor Lee here today to give a presentation of this very interesting topic. Radar will be strategic for many different applications in the near future, ranging from health applications to automotive to many different applications. So we think that this is a really strategic for the research of the next years. So let me introduce Professor Roselli, full professor of electronics of our department, who will give the welcoming address.
Thank you, Valentina. Good morning to everybody. This is a strange commitment for me today because I'm here on behalf of the director of the department and the vice director of this department. So I'm here just as the oldest guy in the department, able to introduce and to give just a brief overview of the department to this audience. So, first of all, let me say thank you to Valentina Palazzi and Paolo Mezzanotte for having organized this event. They took care about all the preparation of this distinguished micro lecture from Professor Changzhi Lee. And the second knowledge is for Professor Changzhi, and I would like to make applause for him for being here and accepted our invitation. So just a few words about our department. Once upon a time, it was the Institute of Electronics at the University of Perugia. We are talking about 35 years ago, and this small unit was composed about 6 sub-areas, namely electronics, electromagnetics, telecommunications, automation, 5 areas, sorry, and measurement, electronic measurement. After some years, the area of computer science was added to these areas of the information technologies. The department changed, the institute changed its status in Department of Information Technology or something similar. I don't remember exactly the precise name. And in the, let's say about, I lost the cognition of time, but about 15 years, in 2013, the department became larger, incorporating all the areas, the cultural areas, the scientific areas of this valley, let's say, including industrial engineering and a small sub-area of civil engineering. So actually, we are a fairly big department in comparison with other departments of Italy. Italy, you know, is a place where we have many universities, not very big, generally speaking. And so in this department, we have these 3 main areas. So industrial engineering, information engineering, and another area of civil and environmental engineering. Overall, we have close to 100 structured personnel working in this, plus all the researchers and temporary personnel for 4, 5, 6 years. So this is more or less the situation of our department, and so I hope that let's say I would like you to enjoy this event, and I would like to welcome Professor Lee for giving his presentation.
Thank you so much.
Okay, so yes, it's time to introduce Professor Lee. Just a few words about him. So he is a professor at Texas Tech University, Lubbock, Texas. USA. And he works on microwave and millimeter wave sensing for healthcare, security, energy efficiency, structural monitoring, and human interface, which is the main topic of today. And he's a fellow of the National Academy of Inventors. He's a Microwave Theory and Techniques Society Distinguished Microwave Lecturer. And he was the recipient of the IEEE Sensors Council Early Career Technical Achievement Award. So we are very, very proud to have you here today. And I also want to say to everybody that don't go away, don't rush after the talk, because we will have a small buffet nearby, which is sponsored by a European project called Ada Corsa, where we are involved. And we also work on radar for drones to basically develop drones able to work beyond visual line of sight. So since it's synergic with that topic, the project will cover the buffet. So, Changzhi, thank you again, and the floor is yours.
Thank you so much, Valentina, for the nice introduction. Thank you, Valentina and Paolo, for hosting me, and thank you, Luca, for the very warm welcome. And good morning, everyone. It's really my great pleasure and honor to be here. And with that, I'll jump into my presentation, get started. So actually, every time when I start the presentation, I start with my daughter, Chloe. And let's see, right here, okay? So before she starts to complain about this, and this video was taken when she was less than 1 year old, like when she was actually even younger than this. And next month, she's turning into 10. So you can calculate approximately when this research was done. So one night, I brought a device designed by my student back home. And after Chloe and my wife went to sleep, I secretly mounted the device on her crib. So if you look at the crib, there is a small device. And the device was looking at Chloe. And on the other side, the device was transmitting data to a laptop. So on the laptop, you can see two curves. The top curve is the time domain raw data without any processing. So it's simply the raw data. And the second one is FFT result. And you can see her respiration very clearly on the spectrum. Okay? So basically, this is the research, and I had to do it secretly because I don't have to get ethic permission from my wife. And this sounds like fancy, but in reality, this technology was discovered many years ago. Back in 1975, as far as I know, it was discovered by Professor James Lin from Chicago, and during that time, he actually applied this to both humans and animals, all right? And what really, I think, inspired a lot of people was in 2002, a group of engineers in Bell Labs was able to integrate the very bulky, huge system developed by Professor James Lin into a single chip. It's gonna be a chip like this. And after that, people realized this entire thing can be done with very low-cost, small portable device. And since then, this research and application really took off, all right? And because of that, personally, I think there are two papers that really inspired myself. One is a paper published by Professor James Lin in 1975 on IEEE proceedings, very prestigious publication. And as you can see over there, at that time, he was able to use microwave instruments to pick up vital signs from animals and also humans. And another paper is like a personal gift to myself. It was published by this group of people from Bell Lab in 2004. So the lead researcher was Amy, and Amy was an intern from Stanford University working at Bell Lab. So she was still a student. Olga, Victor, and Zhenshan, they were engineers at Bell Lab, and Greg was Amy's advisor, okay? So they were able to integrate everything into a single chip and analyze the IQ performance as well as a lot of theory behind that, how range correlation helps to make the signal quality better, okay? And actually in 2004, I just graduated with my bachelor's degree. I was puzzled what I can do for the next step. I read this paper and I was so inspired how this research directly connect semiconductor technology with the human life quality. So I applied to them, and eventually we went to Changzhi's group and did my PhD. Okay. So the fundamental mechanism of this type of detection is actually quite straightforward. Basically, you send out a signal that is unmodulated towards human body, and once the signal hits a human body, I guess I need to get closer to the receiver. Once the signal hits a human body, it's gonna be bounced back. So at the receiver side, you can compare a local copy of the same transmitted signal with the received signal. And by doing that, we call this coherent detection. In the baseband IQ output, the signal phase will be linearly proportional to the movement induced by respiration and heartbeat. Because basically this type of movement will change the length of the signal transmission path and therefore change the signal phase, okay? So very straightforward. If you plot the I and Q data on a constellation graph, then you will see the data point's trajectory actually moves along a circle. If you can find out the angle of movement, then you pretty much read out the vital signs X of t, okay? And what I want to mention is if you look at this equation here, the detection is completely dependent on wavelength lambda. If you increase the signal frequency, you can reduce the wavelength lambda, therefore you make this phase much bigger and you increase the detection sensitivity. So over the years, engineers have been pushing for higher frequency, and nowadays you can easily find out millimeter wave works of this type of application, okay? And another thing I want to mention is for the demonstration I showed in the first video, the transmit power was actually more than 1,000 times lower as compared with the peak power of a cell phone. So this is actually quite safe. On top of that, we are detecting a very slow motion of 1 hertz, 0.1 hertz. Therefore, you can aggressively duty cycle the transceiver. You only have to turn on the transceiver for, let's say, 10 milliseconds for 3 times in every 1 second. Therefore, the average radiation power is even lower, making it absolutely safe for human and animals. Okay? And we call that vital Doppler, vital signs induced Doppler. Another category that really benefits microwave engineers is micro-Doppler effect. And micro-Doppler refers to the Doppler induced by body movement. So consider the case if I have a radar in front of myself and I sit down, and during the moment when I sit down, my body will move slightly away from the radar. So if we monitor the Doppler, you will see a negative Doppler happening over there. But the interesting thing is you also have a small positive Doppler, and that is because of my head. Yeah, because I sit down, my head will lean forward. And after that, if I raise my hand, put down my hand twice, you certainly will see the signature over there. The bottom side has a very similar demonstration. A person walked away from radar, generated negative Doppler, then this person pulled hand twice, generated other signatures, and after that, this person walked back towards the radar, generated a positive Doppler, okay? So with this, industry actually have been doing a lot for different things. So one example is the Google Studi project. And in the Google Studi project, a team of engineers, actually mostly data scientists, they are using an Infinium 60 gigahertz millimeter wave radar to remotely pick up the hand gesture movement. And with that, they can interface with smartphones and other devices. You don't have to touch the screen, you can remotely control that. And as a matter of fact, if you use Google Pixel phone, then the 4th generation Pixel 4 phone has a millimeter wave radar sensor, Infinium sensor over there. And with that, you really can remotely activate your phone, play music, volume up, volume down, do a lot of things. Okay. Unfortunately, the newer version of Pixel phone actually removed this radar because the cost is still relatively high, and the newer generation of Pixel phone really targets for low cost and good software. Okay? But this is actually a very good news for semiconductor engineers, because we have a lot of potential. If we can further reduce the cost, then one day this will come back, and hopefully every phone, no matter what is the brand, can have a radar sensor inside. Okay? But this is actually not the end of story. Google is really excited about millimeter wave radar. So in their new product, their Nest 2, you can actually buy this below 100 euro. Actually, I checked in Google Store Italian version. You buy this at 99.99 euro. And this Nest 2 does not have any camera. Instead, it has a radar inside. And with this radar, you place it near the bed on this table, then it can monitor the sleep quality, your heartbeat, your respiration during sleep without requiring the user wearing any device, okay? And this work is nicely done. So as you can see, they have a pretty high-level brief architecture. They first use the radar sensor for presence detection, find out if we have a person in front of the radar. Then they extracted microdoppler and then applied a lot of machine learning algorithm and eventually found out the data over there, okay? And on the bottom side actually shows one of their test results. So this is not only a product, but also a very good integration with research. This Google Solid team recently published a paper just 2 months ago. And on this paper, they actually published data for more than 400 hours of test. And this is only a snapshot of about 8 hours. And as you can see, the non-contact radar detected results matched very well with ECG data, contact ECG data. Also, the radar was able to tell if this person is facing up, facing down, towards the right or towards the left during the entire measurement period. Okay? So a lot of exciting things are actually going on. Okay? And I mentioned that a lot of this is really due to the modern advancement of semiconductor technology. So nowadays you can integrate the entire benchtop of instruments into a small portable device. And back in 2017, those companies, big companies already demonstrated their radar sensors during the International Microwave Symposium. So for example, over there is the Infinium radar back in 2017, 60 gigahertz. It shares very similar architecture as the Google Solid radar. And on site, they connected this with a tablet, and the Infinium engineers were able to train attendees of the conference within a couple minutes. They can master a lot of commands to interact with the tablet. And in the middle side shows analog device bench, and over there they had a 24 gigahertz radar detecting vital signs of humans. And most recently, Infinium, actually not most recently, already 2 years ago, Infinium delivered this small module, very nice product. You can immediately plug this into your laptop. And using this, a lot of researchers, even data scientists without microwave experience, they can actually do a lot of research, okay? And this nice module is really based on the front-end chip over there, which has 3 receiving channels and 1 transmitting channel, which allows digital beamforming. And this chip also has 2 versions. You can have Doppler radar, or you can have FMCW radar. And today I'm gonna spend a little bit more time talking about FMCW radar as well. But in the meantime, there are so many companies working on that. NXP has their nice solution. Silicon Radar is a German company that produce radar chips above 100 gigahertz. And 2Pi Labs is a spin-off from Professor Niels Pohl's group. They are doing very nice works at hundreds of gigahertz. All right, and the semiconductor industry also works on system-level integration research. So this is a work done by an Italian fellow, Marco Mercuri. So he was first with Dominic, and then he went to IMEC. And over there, he actually led a group of researchers. What they did is they applied IMEC's radar sensor chip, and to set up this environment, they were able to actually monitor multiple people doing different activities in this indoor environment. And when a person sits down, they can also extract vital signs, respiration, and heartbeat. Okay. And I talk about the benefit of pushing frequency up. So here is an example of how we can benefit from higher frequency. In this work, Daniel Rodriguez actually used this 125 gigahertz radar sensor chip from Silicon Radar. And what he did is, because at really high frequency, a little bit of fabrication error is gonna induce a lot of errors in the signal. You're gonna have a lot of IQ channel mismatch and other like frequency dependent distortion. Therefore, Daniel actually implemented analog processing as well as digital processing to correct IQ mismatch and also frequency-dependent distortion. After that, he was able to recover perfect trajectory for motion detection. And from there, he was able to achieve a motion detection sensitivity of 95 nanometer, which is really high. And with that, he pointed the radar towards his throat, and he said one sentence, "I am a boy." So as you can see, over there we have two different radar signal processing methods showing the same spectrogram, "I am a boy." And in the bottom side, he actually used his Pixel 4 phone, but not using the radar, using the microphone inside the phone to pick up the same sentence simultaneously. You can say, "I am a boy," but you also see a background noise, and this background noise comes from the ventilation fan. So obviously, radar has this capability of directional detection. Imagine that in a cocktail party, you can specifically listen to one of your friends. Okay? And of course, this has a lot of security and military applications as well, potentially. You can detect a speech from another room through the wall. All right? So far I've been talking about detecting vibration movement. Another big application for radar is to detect the distance. And if you have to detect distance, you have to use a bandwidth. And the simplest form of using bandwidth to get distance is this so-called FMCW radar, frequency modulated continuous wave radar. Okay? The mechanism is actually quite straightforward. You send out a linear chirp whose frequency increases linearly as time goes by. Okay? And once the signal hits a target, it will be bounced back. Therefore, if you can get a delay between the transmit signal and received signal, this delay, you can get the distance. Okay? Unfortunately, detecting a delay in indoor environment is not trivial at all because you are talking about a delay of a nanosecond level. Okay? Using portable device, FMCW radar solved it smartly. Basically, you can compare the transmit signal and the received signal using a mixer. And then at the mixer output, you are looking at a beat signal, right? And if you know the frequency of the beat signal, then you know the delay, you know the distance. Because we are engineers, we know the slope of the chirp we generated. From here, we can calculate that, all right? So because of that, frequency time domain analysis, time frequency analysis is really important for radar. And here comes the basic flow for FMCW radar processing. So we send out a lot of linear chirps. And for each chirp, we're gonna have a return, the red dashed line, okay? And the mixer at the baseband is gonna produce a baseband beat signal in time domain like that. So if we know the beginning and the ending point for each chirp, we can take out this beat signal in time domain. Then we can do FFT, okay? After FFT, the peak frequency pretty much corresponds to the distance. The peak frequency is the beat frequency, right? So with that, you get a distance. And for radar engineers, they actually call this spectrum as a range spectrum because frequency means beat frequency, and that is basically your range, okay? So with that, here are two textbook type of demonstration. In the first demonstration, we had a person who walked away from a radar and then walked back towards a radar. The y-axis is time, x-axis is range. So you can see the person left the radar, then came back. And in the second demonstration, we had two people walking back and forth. So we had first person walked away from radar, come back. Second person walked towards radar, then left the radar, okay? And in the meantime, you may wonder, why do we have so many vertical stripes? they are actually quite reasonable, because if I do this in a realistic environment, I'm gonna have tables, chairs, they all will reflect signal. They are fixed at a single location, therefore you see vertical stripes, okay? And then we may wonder, is radar really good or bad? You have so many clutters like this. The answer is, this can be easily handled by radar because we have Doppler information, okay? With that, let's revisit the signal processing flow. We have a lot of chirps sent out, and as I already mentioned, the beat signal for each chirp in time domain can be placed over there. So for the first matrix, every row corresponds to each chirp. And for each row, inside the row, we have the time domain response beat signal. And if we do FFT in each row, we convert the time domain into range, right? This is range spectrum, which migrates as time goes by. So this is exactly what we saw over there. The secret is if I do another FFT, instead, this time, my FFT is going to be in vertical dimension, okay? If I do FFT like this, I'm comparing the distance with time, and distance over time is pretty much speed, Doppler. So with that, you can actually end up with both range and Doppler in a dynamic video, and some radar engineers call this ISAR video. So here's a demonstration. We intentionally found out a narrow corridor like this, and we had two people walking back and forth. If we do one FFT, we end up with this range migration plot, which is quite messy because a lot of clutters are reflecting signals. But we do another FFT without any further processing, just two simple FFT, you get the Doppler range video, ISAR video. And from there, as you can see, we had one person and another person walking back and forth, right? And now they are making a turn, and then they continue walking, okay? So all the clutters are actually immediately compressed into this horizontal line with zero Doppler, okay? So you can see two people over there. And another good thing is this dot representing a person seems to be quite messy. You have things around. As a matter of fact, this experiment was done by a radar at 5.8 gigahertz with a small bandwidth. If you increase the frequency, increase the bandwidth, you will have higher resolution, and each part of the body is gonna induce a slightly different Doppler, so you can potentially even see the gesture, the gait of the two peoples, how they are really walking, okay? So with that, as you can imagine, now we are empowered to do a lot of classification because we have range and Doppler. Imagine that I have a radar in front of me, I fall towards the radar, then my distance will reduce. X-axis is range, the distance will reduce, the Doppler will increase, and eventually the signature will disappear because when I lie down, I don't have any radar cross-section reflecting signal, right? On the other hand, if I fall away from radar, my distance will increase and Doppler will be opposite. I'm gonna have negative Doppler, okay? So this is the second scenario. And the third scenario, if this person makes a small jump, then you will see the dot moving around, but this dot will never disappear, okay? So using the same 5.8 gigahertz portable radar, we confirmed this theory. Over there, the top row shows 4 frames extracted from the ISAR video. So you can see the dot started from here, moved in this direction. After a few frames, it disappeared. And this is a case of a person falling towards radar, okay? And the middle row is the case of a person falling away from radar. So the dot actually faded out in the opposite direction. And the final row shows the case of this person making a small step, okay? Obviously, you can tell the difference, okay? So the advantage here is for radar engineers, we have this very nice dot. This dot has Doppler, has range. We also know when this was done, we have time. So radar engineers put the range, Doppler, and time together on this 3D cube. And then you will see the dot moving around for different type of activities. And this 3D cube really enables people to monitor the activity of a human subject continuously. Okay, so with a little bit of machine learning and vote decision, it was demonstrated we can actually use this for a single person. We can continuously monitor this person as this person performed different activities. Okay. All right, and with that, I'm gonna switch to my favorite page of the presentation. So this work was actually done by a high school girl, Rachel, from California. So Rachel stayed in my lab for 7 weeks in one summer. And what she did is she used the radar to look at a person who is driving a car. So when we drive a car, we may look around, we may be very happy, dance with the music, we may pick up a cell phone, right? And one dangerous situation is we may feel sleepy and our head will drop like this. So it turns out, of course, different activities will induce different Doppler signature. So you will immediately see when this dangerous situation happens. Okay? So based on this research, Rachel was able to publish a paper on IEEE Radio Wireless Week as a high school student. And she actually set up a live demonstration on site. I remember that year was in Florida. And furthermore, she competed with a group of PhD students and master students in the best paper competition, best student paper competition, and she got honorary mention award. So this is a time when she got the award from the conference chair, Roshanda, who later on became MTTS president, and also then President Dominic. Okay, so pretty proud of this figure, like 3 ladies over there. All right. And the next one was also done by a high school student, Hannah. And in the case of Hannah, she really loves playing violin. She actually brought her violin from Philadelphia to my lab for 7 weeks as well last year. And I said that, why don't you place the radar, Infinium radar, in your dorm, and when you play violin and see what the radar can pick up. And in her case, she found out, of course, the radar will have different signatures for a person doing different bow movement. Okay? She further collaborated with a group of students from School of Music. So they recruited multiple players and demonstrated you not only can tell the difference of playing different bow movements, you can also tell if a person is playing a single movement right or wrong, slightly different way of playing that, okay? And in the case of Hannah, she further applied the data to machine learning algorithm and found out this type of detection can be automated. And with that, she published a journal paper as a high school student. And this paper only had 2 authors, and I pretty much did nothing. Like when she did the research, I was in Argentina. I set up a daily meeting with her, but she did all the works. So what I want to demonstrate here is radar nowadays is really a great topic, not only for microwave engineers, but also for people interested in computer science, data science, as well as system integration. So a lot of things can be done. And both of them eventually went to MIT, and Rachel already finished her undergraduate degree in engineering from MIT. And she's now in Europe, like she's in the MIT Oxford joint program, continue with bioengineering training, okay? So switch the gear a little bit. We've been talking about using radar detecting moving objects. Another way of using radar is you can actually mount a radar on a moving platform. And this research was also done by an Italian fellow, Emanuele from Sicily. So he considered the case if you have a small radar mounted on a white can, then the radar can actually warn the user before the stick, the white can get stuck into maybe some furniture or hit something, okay? And this is his experimental demonstration. He had the radar over there, and he considered like multiple objects in front of the radar. And he looked at both the range and Doppler information and did some preliminary demonstration over there, okay? But really, personally, I think the challenge of this is you are now mounting your radar on a moving platform. Radar is sensitive to all kinds of motion, so the movement of the white cane itself will complicate the detection a lot, okay? So he actually continued working on that, and in the next work, he considered how to really address the movement of the radar, okay? And in this case, the research was done during the pandemic, so he did it in a nice yard, like near his house in Sicily. And over there, the radar was on a small moving platform, and the radar looked at different things in front of it. The nice thing over there is we have reflection from human, from clutters. Now the clutters is actually quite helpful, okay? Because for the movement of the radar, the clutters will behave the same. Their signal reflected will pretty much demonstrate how the radar is moving, right? So based on the range information of FMCW radar, you can extract the signal from clutter 1 and clutter 2, although you don't know if they are clutter or humans. But you can run a correlation. If you run correlation for the range being of those two objects, you will immediately see the two clusters has a very high correlation because pretty much they are reflecting the same radar signal, okay? But the correlation between cluster and human is really bad. There is very minimum correlation since the human not only is observing the movement of the radar, but also the human itself has its respiration and heartbeat. So based on this difference in correlation, he was able to extract the respiration and heartbeat of this person in the case of the slightly moving platform. So this is really pushing forward if the radar has movement. All right. And with that, I will return to the topic of microwave front end a little bit. And next page actually highlights the importance of friendship and having lunch among friends. So Professor Jason Hong is from Taiwan, and his expertise is not biomedical application. He did nothing about biomedical radar. He went to Changzhi's lab in Florida 1 year, stayed there as a visiting professor for 1 year because they are friends. So one day they went out for lunch, and Changzhi explained to Jason how the biomedical radar works. Basically, you send out signal, you get bounced back signal, you compare the two. But Jason is an expert of injection locking oscillator. He immediately realized, wow, this is so similar to the work of injection locking oscillator. Injection locking oscillator, basically, if I am injection locking oscillator, I have a strong signal near me, then my oscillation frequency could be sort of influenced by the incoming strong signal, and at the end of the day, the two signals, myself and the incoming signal, will be oscillating at the same frequency, okay? So Jason immediately asked his student, nowadays also a professor, to set up the experiment in Taiwan, and what they did is they had an injection locking oscillator, and this injection locking oscillator sent out a free-running signal. But once the signal is bounced back, you already have the information of vital signs. And that signal is going to inject lock your oscillator. And then the oscillator is going to generate a baseband response corresponding to the vital signs. Okay? The advantage of that is they have theoretically shown the sensitivity of this type of injection locking is really, really high. And because of that, they don't need an amplifier in the receiver chain. That is one advantage. Another advantage is you can easily combine the two channels into one channel. Therefore, you only need one antenna for the entire system based on injection locking. Okay? And furthermore, they actually played a lot on locking mechanism. So they found out you can actually set up two injection locking oscillators. Each oscillator will be inject locked with itself initially, but eventually the two will be mutual locked. This signal will influence that and vice versa. And if we do that, basically, you are looking at human subject from two sides of the body. So now imagine that I have two radars, one side here and another over there. If I slightly move towards one radar, I'm moving away from the other radar. Therefore, I have a positive Doppler and a negative Doppler generated. Okay? But if you think about the respiration, when my chest expands, it's moving towards both radars, and both are positive Doppler, right? So you have differential signal pattern over there, and based on the differential signal pattern, they can actually cancel out the noise induced by random body motion, and they demonstrated they can detect vital signs even if a person is walking slowly on a treadmill. So this is another advancement to make this biomedical radar more practical. And so since then, they have been working a lot on different things, and most recently, they added MIMO and digital beamforming into their injection locking radar, and they demonstrated a very impressive result over there. They have 3 human subjects that are really close to each other, okay? And then they use a radar to look at the 3 human subjects. They can get a rough image of the 3 and find out where the chest is for each person. And from there, they were able to extract heartbeat and respiration, okay? Heartbeat and respiration for each individual, all right? And this is a new result recently published. On the other hand, there is another group, Professor Michael Wu from Rutgers. They've been working on using this injection locking architecture, but try to integrate that into a single chip. So here is a sort of fun project. They integrated this injection locking based oscillator and the entire front end into a gallium arsenide process. And now the transceiver works at 85 gigahertz. And they also demonstrated reasonable detection of respiration and heartbeat using this single small chip. Okay? And another popular architecture being researched is this 6-port architecture. 6-port is actually a very, very nice architecture from microwave engineering point of view, but researchers actually applied this into biomedical radar and motion sensing radar as well. So this is an example of Alex Kopin's group in Germany. They use this 6-port architecture working in millimeter wave range to first detect heart sound. Basically, heart sound represents more detailed information as the heart pumps. You can see more information. This is closer to ECG type of thing. And moreover, they used this radar to look at different locations of the body. If you can detect this pulse from the neck and also from the heart, then you can calculate what is the time used for the pulse to transmit from one location to another location. And with that, you can immediately calculate the pulse wave velocity. And with pulse wave velocity, medical doctors can correlate it with blood pressure. So from there, there is a possibility to also use biomedical radar to detect blood pressure. All right, so with that, I'll shift the gear again, talking about a very different detection mechanism. So far, we've been talking about detecting the natural response from targets. But another big category of radar is to detect electronics, and that is called nonlinear radar. And this is not new either. So this, I'm pretty proud of Europe. So this was again made possible and successful. Like we have this European company, Reco, and this company started in the 1970s, 1980s. And the story was that the inventor of this really likes skiing. So once in the 1970s, he was buried underneath avalanche. But he was lucky, he was found out by people. And after he was dug out, he applied his engineering skills to find out a way to protect people who love skiing. And eventually, he started this company, became both rich and famous, all right? And how this works is everyone is going to wear a tag, and what is special about this tag is there's no battery inside. And this is not RFID either. This is actually quite simple, much simpler than RFID. Inside the tag, there are 2 things. One is a diode, okay? And another is a piece of wire, okay? With a diode, you can generate harmonics. So the diode is going to generate second-order harmonic of the incoming radar signal, okay? And the piece of wire can make antenna. And the antenna is going to radiate the signal back towards the radar. And in this case, the radar receiver will be specifically looking for response at second-order harmonic. And with that, you can differentiate between person wearing the tag and other clutters, okay? And in recent years, people noticed This type of tag is dual band. You have incoming signal at one frequency, return signal at a totally different frequency. So the design complexity is not that simple either. So people looked into intermodulation as well. And in the case of intermodulation, you send out two frequencies which are in the same band, and the nonlinearity is going to generate a third order intermodulation in the same band. And that being said, your tag will be a single band tag, and the tag will be even simpler. Okay? But of course, nothing is for free. If you use that, your transceiver will be more complex. You've got to specifically select one of the third order returns, and you have to reject the fundamental return as much as possible. But the good news is, from the transceiver side, we have more space to accommodate more complex transceiver front end to carry out this job. Okay? So with that, I'll show some very simple demonstration. The first one was also done by an exchange student. So Will was from Ireland, and he was undergraduate, not high school this time. So Will stayed in my group also for two months in the summer. And what he did was specifically playing with wire. So he pretty much wrapped up wire to make dipole antenna. And in the middle, you have a circle to provide the DC short. And then he added a diode over there. After that, he taped the entire thing to his wrist. Okay? And with this, the intermodulation radar at 5.8 gigahertz was able to pick up his wrist pulse. Okay? He also published the paper in Radio Wireless Week and competed in the paper competition as undergraduate student. Okay? And Ashish was a PhD student, so Ashish designed a slightly more complex system, but still it's quite simple. He has multiple antenna elements, and each one was driven by a diode, and this entire thing was on flexible substrate. He put it into his jacket, and with that, this tag was able to significantly boost the signal of heartbeat. Because one challenge for vital signs radar is that heartbeat signal is normally much weaker than respiration signal. So you want to really boost the signal of heartbeat in order to avoid the interference from the harmonics of breathing signal. Okay? And in recent years, there are also groups designing small chips. They try to use that to track insects. All right? And Professor Niels Paul's group in Germany, they also work on harmonic radar. And in their case, they work on semiconductor chips at really high frequency. So this is one of their recent work. They had a 60 gigahertz harmonic transceiver, transmitting at 60 gigahertz, receiving at 120 gigahertz. And this is their tag. So they have very nice chips designed. And back in this summer, during IMS, International Microwave Symposium, they also showed they actually placed this small tag along the leg of a patient. And with that, they can precisely monitor the angle of the joint for a patient who is recovering from incidents. Okay? And in that case, their radar was placed over their radar sensor. And you see a lot of complexity over there. Actually, those things are reflective tag for infrared system. Basically, they compared the outcome, the detected result of the radar with infrared system. But the radar is really simple. You only need two tags, then you can find out how the joint is moving. Because you have another anchor over there, the radar, so you have 3 points, you will know the angle precisely. Okay? All right. And the next page, starting from here, I will quickly talk about maybe a few application case studies. The first one is the only page I have on ultra-wideband radar. So there's a group in China, like this group, they have been using ultra-wideband radar, sending out a very wideband pulse. And the advantage in that case is your wideband pulse can help to penetrate through debris. So in their research, they are very practical researchers. So they really look at how do you find out people buried underneath those earthquake debris. And they have been doing this for more than 2 decades. So this is their true product. And what was impressive was in 2008, there was a major earthquake in China, level 8, and their device was used by the government and successfully saved a lot of lives. Okay? But there was also sad story. In one case, like a group of people had been they saw signal from the radar. They've been digging for hours, and eventually they dug out a chicken, not a human. Okay? So if you follow up the research by this group in recent years, they've been focusing on how do you differentiate between human and animals. And another thing is how do you tell the orientation of the person underneath? Because you've got to know the orientation of this person, and with that, you can select the best angle to dig in order to not really hurt this person. And with that, they have to integrate a lot of signal processing, machine learning into their system. Okay? This one is a story of animal detection. So this is a long story. So when I was a PhD student, we filed several patents with Changzhi, my advisor. Later on, the patents as well as the 5.8 gigahertz radar design was licensed by a company. And the company made a device called Vet Guardian, and this is becoming popular in the US. So at vet hospitals, the nurse actually use it to point at animals. And the group of people really has done a lot of customer discovery, and they found out a very unique application case. When the nurse want to know the vital sign of animals in critical situation, they don't want to open a cage. One thing is it's dangerous. A second thing is they don't want to disturb the animal. So the device actually can be manually pointed towards the animal, and the device also has a thermal camera over there. So with that, you can point towards the chest and read out the best vital signs whenever you need it. It's not continuous monitoring, but it's quite helpful. So in September, the company actually finished their acquisition by a very big public company, and I believe the deal was around $18 million. So very encouraging case, but not on humans. And the entrepreneur of this device now, because their company is bought, they actually is moving towards human detections. Okay. All right, and people also use this for sleep study, as Google Solid team has done. In this case, this is a Chinese group in Nanjing, but the good thing for them is it's relatively easier to get those permission for clinical study. So they actually have carried out a lot of clinical study in collaboration with hospitals for sleep monitoring for patients in hospitals. This work is done by the guy, he was my student who designed the device for my daughter, and later on he went to Google Solid, and he was the person who put the Infinium radar into the Pixel 4 phone, and after that he returned to Shanghai and became a professor, and his team also collaborates a lot with hospitals. And this research is pretty impressive. Like they used a radar to monitor a patient, and this patient had a heart problem, so she just went through a surgery, open heart surgery, and she was completely sleeping. And during the recovery process, they used the radar to monitor her heartbeat, and definitely the heartbeat is different from a normal person. They compared the results with medical instruments, and turned out the performance was very good, quite encouraging. And of course, they found a niche. In this case, the patient was not moving at all, like the patient was basically sleeping. They also applied this to preterm babies. So this was also done in hospital. They mounted their 24 gigahertz radar in this box, looking at a preterm baby. And what they found is important, but also intuitive. Basically, apnea can be detected much earlier than the drop of blood oxygen. Of course, if I stop breathing, my blood oxygen is gonna drop. But the advantage of radar is you capture the reason, right? You don't wait until blood oxygen drops. This is definitely an advantage of biomedical radar. Once the baby stops breathing, the radar can already trigger alarm to the health providers. All right. And the same group actually recently, very recently, also applied this for continuous blood pressure monitoring. But in this case, they are again sort of cheating. They are collaborating with hospital using radar to monitor a patient who was basically not moving, put into sleep, and during the process, they were able to get amazing results, even to extract the blood pressure as compared with medical instruments. All right. So with that, here comes to the end of, near the end of my technical presentation. So today I actually talk a lot about FMCW radar, frequency modulated continuous wave radar. But if you look at the FMCW radar waveform, it looks like that. This is a simple analog waveform, right? So for communication experts, this is sort of 1G communication. And nowadays, actually, recently, the industry, automotive industry, is very interested in PMCW radar. They apply digital modulation to the phase of signal, but it's really difficult, very challenging, because the speed of modulation has to be really high in order to get sufficient resolution, okay? And this is sort of 2G communication. So I view this as a really exciting news for researchers, because there's a long way for radar to do. There's a lot of R&D efforts that can be done by talents like the students here in this room, all right? So basically, I think for modern smart radar, it really needs a lot of contribution from people with expertise on hardware, algorithm, as well as system integration, okay? And I only scratched the very surface of some applications. But there's a lot of works on imaging security, diagnosis, also water monitoring. We have experts here in this room. You can use radar for structural health monitoring to monitor bridge and turbines. We also have works over there. And Niels Pulse group actually has been doing a lot of material characterization above 200 gigahertz. Okay? So definitely it needs a lot of contribution from talents in this room, all right? And with that, I will only spend 2 minutes to do a classical advertisement for MTTS. So MTTS has this graduate fellowship program. It has 2 categories. One is general category, another is medical category. And I'm very proud of that. We have a separate medical category, because this category traditionally has a large number of female students applying to it. And this year, we actually have the first ever time we have more female applicants than male applicants in the medical category, okay? But for the 2 categories, general has 12 awardees every year. Medical has 2 awardees every year. And the benefit is you have 6,000 cash prize. You have travel support up to 1,000, but this number will be upgraded to 1,500 very soon after November. It's gonna be changed to 1,500, okay? Money is not big, but the most important thing is how prestigious it is. It's really a prestigious award, and a lot of awardees became really successful in their career, including Valentina. I'll show you very soon, okay? And if you are undergraduate or master's students, you are really encouraged to apply to the undergraduate, pre-graduate scholarship. The money will be increased to $2,500, and travel support will also be $1,500. And this scholarship has 2 cycles every year. One is in April 15th, and another is October 15th, okay? And all the awardees will be published on IEEE Microwave magazine. So your name, your photo, your advisor's name, project name, they will all be published on IEEE Microwave magazine, okay? So with that, my favorite page over there, I randomly grabbed some photos of past year awardees. And the way I said random, we actually have a database. We keep track of every awardee through LinkedIn. So as you can see, after this random selection, I got those photos, and then I did a little bit of work on those photos. Those persons in red, they are already either professor or researcher educators in higher education institutes. So I believe you guys all recognize who she is, right? Yeah, and several examples, like he's now with the University of South Florida. She's a professor in Chengdu, China, UESTC. And this is a professor at Rice University in the US. And he's now a professor in Germany, Fabian. And this is a professor at Stanford University. Now, he's a professor, I have to be more specific, like he's still assistant professor, he's associate professor at MIT. And Changzhi is who I mentioned, like who put the Infinium radar into Google Pixel 4 phone, and he's now a professor at Shanghai Jiao Tong University. Jack is in Finland, and this is Marco, and maybe some of us recognize him. Like he used to work with IMEC, and now is a researcher in Italy. He returned to Italy. And those green boxes are already second or third generation of the awardee, which is quite impressive. For example, she is a student of him, and he's actually the second generation already. Like he's a student of myself, and I got this award in 2008. So when I got it in 2008, I was working for a company, so my colleagues in my company told me this is a great award. All the awardees he knew eventually became professor. And I didn't believe it. I didn't believe it, but it happened to me somehow. All right, so definitely this is a really nice program, and I strongly encourage every student here to apply, and every professor, please encourage your student to apply. Okay, so with that, I have finished all my presentation. There are several photos of Texas Tech University. I warmly welcome you to visit Texas Tech University in West Texas. So in movies, Texas is very hot. Indeed, we are very hot, close to desert. But in the winter, sometimes we also have snow. All right, so with that, thank you so much.
Thank you very much, Changzhi, for this fantastic, very interesting talk. So now we have some time for questions. Are there any questions? Maybe I can start. I can just break the ice. So my, oh no, there's a question.
Simple question. I saw that the range is the maximum range on the presentation was 12 meters. Is there some studies made on different kind of topics with an extended range, like hundreds of meters and stuff like that?
Yeah, that's a very good question. Thank you. So thank you very much for the question. Regarding the range, normally like in my research or the researchers I work closely with, we look at indoor application. So it's somewhere between 1 meter and 10 meters. But I do have seen long range, sort of relatively long range detection. The group in China who is doing earthquake search and rescue research, they also have another branch of research of detecting voice using radar. And in that case, their extreme cases, they use the coil antenna, which is really a long coil antenna with high directivity. They were able to actually pick up speech across a football field. So yeah, definitely if you increase the power, you increase the antenna directivity, that is possible. And obviously, you know like what type of application they are targeting at for that range. But that is possible, and a lot of contribution with antenna from antenna experts would be appreciated for longer range.
Any other questions? Yes.
Yeah, Changzhi. I am curious about experience of mounting. I am curious about your experience on mounting radars on drones. Since can you discuss a little bit the effect of propellers? Since of course the backside lobes of the antenna can see the propellers, but also there is a kind of air wave. And also radars are able to detect the wind, no? The velocity of air. So what is your experience in this field?
Yeah, thank you very much for opening another discussion. So I'll start from the second question about detecting wind, because I'm pretty proud of that. Texas Tech has a group. I don't directly work with them. They are from a totally different college. And what their expertise is to use radar to monitor wind. And there are actually at least two big groups in the US. One is Texas Tech, and another one is in Oklahoma, University of Oklahoma. They have large radar mounted on trucks, and they can monitor. Oklahoma is well known for tornadoes. They can monitor how a tornado moves, okay? But as a matter of fact, radar has been used as weather radar for a long time, right? But state of the art is to use radar for relatively shorter range detection. For example, you can use radar to monitor wind in a wind farm with a lot of wind turbines. So what was discovered is that in a wind farm, you have rows of turbines, right? But the first row of the turbine, because the wind has to propel the turbine in turn will also change how the wind is facing, how the wind is moving. So if you can monitor the direction of wind with millimeter wave radar high resolution, you can know how to optimize the angle of the turbine. Each row of the turbine will have a slightly different roll angle. And with that, you can optimize the overall efficiency of the entire wind farm. So that being said, definitely monitoring wind is a very good direction to look into. And another question is regarding drones. So I think that's an excellent question because we know that conventional radars like fighter jets, they all have this phased array in the nose of the airplane. So almost every airplane, especially military airplane, has radar inside. But why don't we have radar in drones? Quite naturally. We have advanced semiconductor technology. We can integrate smaller radars into drones. So there are actually groups of people doing research on that. But one critical thing is, as already mentioned, the propeller of the drone itself is moving fast, and that can induce artifacts, interference into the detection. So my guess is the mounting of the radar is pretty critical. You've got to mount it in the right way. And knowing the location, precisely knowing the location of the drone is also critical. Because the really nice thing about drone and radar is you can have multiple drones. Each one carry a radar. Then you can synthesize a very large aperture. And based on that, you can have a really high resolution image. But the challenge over there is how do you precisely know the location of each radar or each drone, as well as how do you synchronize all the radar sensors. Synchronization, wireless synchronization is another thing to look into. So that's a fantastic area. Yeah. Thank you.
I wanted to mention that also people that are connected online can make questions through the chat, and we will monitor it. So if you have questions, even from online, you can make them. So any other questions? Yes.
Thank you so much for your presentation. It is very interesting. So I have just a question about the frequency. I see that you mentioned 5.8, and then you go up to 122. What do you think about 24 and 76? Is it used for this type of application, or it's because something is allocated for automotive, so the researchers are going more to use another frequencies?
Thank you for the question. Actually, we use 24 a lot, 24 gigahertz, because 24 is really a sweet spot. You can do chip design, but you can also do board level design. And 24 gigahertz, you can design really low cost boards. Very low cost board, because if you can properly handle the loss, you can even use a relatively low cost substrate as well. But that's a sweet spot for microwave design and IC design. Like people can meet in the middle over there. So that's really nice. And we actually had several different versions of 24 gigahertz radar. Regarding 77, we haven't done that too much, but there are people doing that. I think the main reason is 77 is now really used extensively by automotive industry. And over there, it's already very crowded. Imagine the future traffic junction. You have multiple cars, and each car will have multiple radars. So interference is something we've got to look at 77 gigahertz. So personally, if we want to move to even higher frequency, I would probably look at 60 gigahertz, unless if I have to look at automotive application, then I look at 77 gigahertz. And another consideration about frequency is, although you get higher sensitivity, actually, if the frequency is extremely high, turns out, think about the equation, cosine, inside you have 4 pi xt over lambda. If lambda is too small, the phase is too big, the phase is going to change over several circles. Then you will have codomain problem. You will also have a lot of nonlinearity on the directly demodulated spectrum. So you've got to do more demodulation in order to get rid of those harmonics due to high frequency. So for higher frequency, there are also tricky things we have to take care of. So actually my personal favorite is 24 at this moment.
Thank you for your very inspiring presentation, first of all. Then I have a curiosity. I have seen that you also show a method for seeing the blood pressure, considering the propagation of the pulse of the... So it is necessary to stay very close to the radar, or it is possible also to think to a system in which you can detect also for people that is walking or something like that? This is the first question. Then I have another, very short. And then if you can comment also the possibility of use artificial intelligence together with these systems in order to obtain alarms. For example, if you are monitoring something and by artificial intelligence, if it is possible to create, to use the artificial intelligence to have alarms or something like that. Okay.
Thank you. Thank you for both questions. I think they are wonderful questions. For the first question, can we detect, for example, blood pressure from far away if a person is walking? I think that's definitely a dream of many biomedical radar or radar sensor researchers. I haven't seen anyone who can do that yet, but that is definitely what we want it to happen. And this is a good news. So that means there could be a lot of researchers working on this, could be a lot of papers published, a lot of job opportunities. But for now, blood pressure is strictly limited to stationary case because, right. And also antenna is important. You've got to be very precise, point at 2 points, and then you calculate pulse wave velocity. But there are also researchers not using 2 points. They only look at 1 point. And it turns out from medical point of view, the waveform, the shape of the waveform can also sort of tell blood pressure. We don't know how much correlation it is. This is still a medical puzzle. But there are a few papers on that. Like only look at 1 point and try to figure out the blood pressure. Yeah. So that's the first question. Second question is about artificial intelligence. So nowadays, if you look at the research, a lot of things, I simply say we apply machine learning, but like behind the scene machine learning, how do you apply and what algorithm you use? This is a very big category, big research area to look into. I think extremely good news is the semiconductor industry really makes it easy for even computer scientists to do research with radar. You buy this Infineon 60 gigahertz module, you plug into the laptop, you can immediately do a lot of wonderful research. This is a good thing. But on the other side, I really want to encourage even for signal processing experts, computer scientists, really collaborate with microwave engineers to make sure what we discovered or worked out is feasible from physics point of view, that is doable, or fundamentally this is correct. We do need to have a very good understanding of the physics mechanism behind it to make sure the machine learns the right thing, not the wrong thing. Thank you.
Thank you again for your presentation. I found your work really, really interesting. And a similar question regarding the detection of the respiration and the heartbeat. I was wondering if it's possible, even if the subject is running or in movement, maybe with the usage of passive tags or something similar.
Right, great. So thank you for the question. The question is it possible to really detect respiration, heartbeat if the subject is running or moving? I'll say from research point of view, there are already some simple demonstrations. For example, the injection locking group in Taiwan, they had one paper like a person was moving on a treadmill. They can extract signal. But I don't think this can be readily applied yet. There are we can get good case that we get signal, but a lot of times the movement could be too big to really extract useful information. So I appreciate you mentioned this important thing, using a tag. With a tag, definitely you can enhance the signal quality a lot. If you have a tag, either RFID or harmonic tag or nonlinear tag, put it close to the shirt or to the chest, that can significantly enhance the signal detection. And then another question is, how do we engage the customer? Like people really need a culture or they need to accept the technology. So a lot of things behind the scene really need contribution from entrepreneurs. People have customers in their mind to convince or educate other users. This is really a reliable technology. Or not reliable, useful technology. Right?
Are there other questions? So I have a question. So my question is very short. So which is the most challenging thing that you see, in terms of hardware, to actually improve these systems? So what do you think is more, the next challenge that you have to, either hardware or signal processing that we need to tackle, in your opinion, to really, move forward with these radar systems? I hope it's not too deep.
Yeah, thank you. That's actually a wonderful question. So I think one big challenge is definitely the directivity, the radiation. Antenna, if you talk about MIMO, it's going to be the entire antenna front-end system. Because obviously, radar, a lot of times when we talk about radio frequency, people want to compare with cameras. And our limitation is that our signal broadcast moves without a high directivity. If you really want to precisely know what's going on at one single direction, then high directivity and this adaptive control of the beam to point towards where we want, this is something really needs to be strengthened from RF radio frequency point of view. So my personal feeling is that really needs a lot of contribution.
Thank you very much.
Thank you.
Are there other questions from the audience? Okay.
Thank you, Valentina. No, I have a comment more than a question, if I can. I don't know if there are other questions more specific. No, my comment is about, I am really impressed about this presentation because it is, so to speak, paradigmatic for the development of the electronics. This comment is mostly I hope it's beneficial for the students, because of course who is working since years in the field knows actually this aspect. But for our students, I would like to stress the fact that radars are systems that, historically speaking, were considered and are always considered very, very critical systems, top systems from all points of view, economic, technological, research, and so forth. Consider, for instance, that in the World War II, the radars somehow is considered one of the reasons why the Royal Italian Navy was less strong than Royal British Navy. So the importance of these systems, for instance, in defense application was really, really important. And I remember, let's say, in the 80s, early 90s, we saw the first radar system appearing on the sailboats. So, but they were still systems very, very expensive, very technologically soundy, let's say. And now we are saying that we are seeing that radar systems are appearing and are present in the daily life. So we see radar systems in surveillance for kids, in many applications, very consumer applications, with frequencies that are still high, because I saw on the market radar front ends at 60 gigahertz at the cost of a couple of let's say, a couple of tens of euros. And so this is a kind of destiny that all the electronics is experiencing, of course in the area of consumer electronics and daily life applications. I would like to stress this to our students, because it's something that we have to consider, also to think to the implications that this trend has in our research, in our study, and in our, let's say, life of future engineers, so to speak. So thank you again, really, for this opportunity to experience these new trends for the electronics.
It's my great pleasure. Thank you.
Yeah. So I think that also now we can move to the buffet, and if there are other questions, Professor Lee will be with us still for a few hours, so it will be a good opportunity for everybody. So yeah, thank you again, Professor Lee, and thank you everybody, for being here. I hope I'm sure this was a very interesting talk, and I hope this will inspire you and will be, something that you will take, we will consider in your future career.
Thank you so much.
Let's go.
Thank you.